Hello, everyone. I am Anurag Kumar. I'm going to present our work using RLHF to align speech enhancement approaches to mean opinion quality scores. This is a joint work with Andrew Perrault and Donald Williamson from Ohio State University. Speech enhancement is a process by which we remove unwanted background perturbations in an audio signal to improve our ability to perceive and communicate information effectively. It's usually done by training a deep neural network. Majority of the contemporary works use a mean squared error-based training objective. However, it introduces two major problems. First, the mean squared error-based is shown to be a suboptimal training objective for speech enhancement. And secondly, the metric used to evaluate such systems are different from training, and thus there is a gap between training objective and evaluation metrics. Through this work, we hope to bridge the gap between the training and evaluation metrics by using a reward model that estimates human quality ratings. We also introduce a novel model-agnostic RLHF framework that aligns speech enhancement models towards subjective human quality ratings using the SET reward model. I would move on to discuss our proposed method. In conventional speech enhancement approaches, the training data usually consist of paired, noisy, and clean reference signals. The noisy signal becomes the input to the model, and model is usually trained to predict a mask, which is usually applied to the input noisy signal through some predefined transformation to produce the enhanced signal. The transformations themselves can be based on the magnitude of the signal or can affect both magnitude and phase of the noisy signal based on the mask output of the model. The training itself is usually done by reducing the mean squared error between the predicted enhanced signal and the clean reference signal. We would like to interpret this speech enhancement problem as a reinforcement learning problem. In this case, the set of all the time frequency representations of our audio signals, be it noisy, enhanced, or clean, becomes the state space S. The predicted channel-wise mask from our speech enhancement model can be interpreted as actions. The speech enhancement model itself becomes our policy pi, as pi can be any function that maps states to actions. We would use f theta or pi interchangeably to refer to our speech enhancement model. The reward function maps states to a scalar value. We define a reward model R with parameters phi, which maps any time frequency representation or state to a scalar value. We define the pre-trained speech enhancement model as pi theta SFT for supervised fine-tuning, and the RL fine-tune model as pi theta RL. The mask prediction from a policy is deterministic. To calculate policy gradients, we need this function to be stochastic. We achieve this stochasticity by adding a fixed variance, zero mean Gaussian noise to the mask. This enables us to calculate the log probabilities of the predicted actions or masks, which are essential for calculating policy gradients. In an RLHF framework, a reward model is usually trained to estimate human preferences. NISCA is a network that was trained to estimate human mean opinion scores of an audio signal. Given the similarity between the application of NISCA and the definition of a reward model, we chose to use NISCA itself as our reward model. We refer to this model as R phi, where phi are the NISCA model parameters. We define three different reward signals. RMOS is the relative difference of the estimates of subjective audio ratings between the RL fine-tuned policy pi theta RL and SFT model pi theta SFT. RPES is the relative difference of objective audio quality score between the RL fine-tuned policy pi theta RL and SFT model pi theta SFT. R combined is a sum of the previous two reward signal RMOS and RPES. While we would like to train our policy such that the reward increases over the course of multiple episodes, we would also like to restrict any big changes in the output distribution between the SFT or the pre-trained model and the RL fine-tuned model to avoid any overfitting. Thus, we also introduce a KL penalty in the overall objective to be maximized. J theta defines the objective that we would like to maximize over the course of training. This would ensure gradual reward increase while avoiding any major output distribution change. Beta controls the weightage of KL penalty in this objective. We use the well-known policy gradient algorithm, PPO, to fine-tune our model. PPO restricts big parameter updates by clipping the step size using the variable epsilon. The PPO loss is a weighted loss in the direction of J theta. The step size is defined as the ratio of the log probabilities of an observed mask given the noisy input before and after the training step. If the step size is greater than the epsilon, we clip the value so that the update remains within the predefined bounds. Our overall loss is a weighted sum of the channel-wise mean squared error between the clean and the enhanced signal and the PPO clip loss. We would now like to discuss our experimental setup. We use the publicly available voice bank plus demand dataset for training. We use the seen test set of voice bank plus demand and the unseen test set of LibriMix to evaluate a proposed method. We use both time domain and time frequency domain speech enhancement methods as baseline for our comparison. To show the generality of our framework, we fine-tune two very different models, metric GAN and CM GAN, using our RLHF framework. While metric GAN predicts a magnitude mask, CM GAN predicts both magnitude and phase mask. Now discussing the results. Table 1 shows the comparison of baselines with our proposed methods. Metric GAN PPO and CM GAN PPO are the RL fine-tuned models from their respective pre-trained checkpoints. We propose the use of RMOS as the reward signal, and the results shown here refer to the models fine-tuned with RMOS as the reward signal. While we observe little to no change in PEST, we see a consistent increase in SSNR and SISDR after the alignments. Story remains largely invariant to the fine-tuning. The models were trained on voice bank plus demand dataset. To see its performance on an unseen test set, we used the LibriMix dataset to evaluate our method. We compared the two SFT models to their respective fine-tuned counterparts. We see a consistent increase in the NISCA-MOS scores after alignment compared to the pre-trained baseline. Figure 2 here shows the increasing trend of the NISCA-MOS scores over the course of 1,000 episodes for both metric GAN and CM GAN PPO. We conducted an ablation study to observe the effects of PPO loss gradients on the overall performance of the speech enhancement fine-tuning. We also wanted to study the effects of using different reward signals during training. The table here shows the comparison of different reward signals using objective evaluation metrics and NISCA-MOS. For CM GAN plus MSE, we further trained the CM GAN baseline checkpoint using the MSE loss defined in the original training framework. We intentionally kept the learning rate lower than the one used in the original recipe. This was done to ensure convergence of the loss. We used both MSE and PPO loss to fine-tune CM GAN PPO. All fine-tuning was done for one epoch. We observe that the CMGAN PPO with all the different reward signals have, on average, better evaluation metric scores than the CMGAN plus MSE or the CMGAN baseline. Thus, the inclusion of PPO loss leads to better convergence. Among the three reward signals, we observe the best PES score with RPES and the best NISCA MOS with reward RMOS. But this was expected. However, we achieved the best SSNR and SISDR with the reward RMOS. We also fine-tuned a model with R combine or RCOM, a sum of which is a sum of both RPESC and RMOS. It gave us a better fine-tuned model than the baseline. However, achieved subpar metric scores when compared to models trained with either of the two other reward signals. Overall, we conclude that the use of RMOS as the reward signal is optimal. Thus, to summarize our presentation, we present an RLHF fine-tuning framework for speech enhancement. We also conduct an ablation study to quantify how policy gradient affects performance and to assess the effect that reward functions have on policy gradient optimization. Through objective and MOS-based evaluations, we show our proposed models improve performance and over baselines on multiple data sets. Thank you.